Week 14, lesson 6. Okay, so this lesson is going to be on regressions, and to do it, you're going to have to be able to use Desmos. So my video is going to kind of go back and forth between writing on the paper and showing you how to do stuff on Desmos. So what you're going to be given is some data, okay? And you're going to plot it in Desmos, and it's going to be just a bunch of dots. All right, and sometimes you'll see something that looks very, very clearly like, I don't know, maybe like a line or like a quadratic function. But then there's going to be other times when you're not exactly sure what shape would best fit the data. And so you're going to have to try some other regressions. So the first thing that you're looking at here on this paper is I want you to know what these sort of look like. So some of them you know very, very well, maybe others not so much. So for linear, you might be given a bunch of dots that look like this. And then it's kind of obvious that a line would go really nicely through them, right? Or maybe they kind of go downward like this, all right? But a line might be what fits the data best, okay? So for quadratic, it might be an upward facing parabola or a downward facing parabola, depending on what the dots are. Cubics look kind of like this. Maybe they look like this. They don't have to have, I mean, it could just literally be sort of more like that. Quartic can look like this, like this, like this, like that. All right, again, there's a lot of different options. But the good news is Desmos will do all the work for you. Logarithmic look sort of like this or like this if they're reflected. Exponential can have a couple different looks. Like if it's exponential growth, it looks like this. But if it's exponential decay, it looks like that. Trig functions, the only ones that we're going to cover are sine and cosine, which both have the same shape. They've just been phase shift from each other. And then logistic, you may have never heard of, but it's kind of like if you think something's going to be exponential and it's growing, but then you know that it's impossible for it to keep growing. All right, at some point it has to taper off. For example, population. All right, yes, I realize population is growing, but at some point the earth will not be able to sustain every single person that wants to be born, and it'll have to taper off in some way. Okay, so let's scoot this up. I'm going to jump over to Desmos and show you how to graph this. And then I'm going to kind of jump back and forth and show you how to write these equations. Okay, so now that I'm in Desmos, let me show you how to get this data to graph. All right, so you're going to come up here to the little plus sign and you're going to add a table. Right, and so I'm looking at this table that's entitled years and average movie ticket prices. So I'm going to start with 1910, right, 1920. I'm going to keep going down. And then obviously over here in the Y column, I'm going to put the movie prices. So, right, so 0.07 and 0.27, all right, etc. So now that I have all the data, and notice on the graph itself over here, notice I'm not seeing anything. All right, so I am going to hit this little zoom fit button, and there's the data. Okay, there's the data. So now I'm reading the thing, and it says come up with a linear regression and an exponential regression. So let me show you how to do that. I'm going to come over here to a new line. Okay, so to do this linear regression, I need to type in the equation of a line, but without an equal sign. I'm going to have to type it in with a tilde. All right. And second, probably most important thing is up here. See how these have an X1 and a Y1 in them? In my equation, I need to remember to put those little subscripts or it's not going to work. So let me start with Y sub 1 is approximately, right? That's what the little tilde is saying. MX sub 1 plus B. All right. So Desmos comes up with this line that it thinks is the best fit mathematically for your data. All right. Now, the equation, right, because on the paper it's asking for the equation. You can see it down here. Here is the M that it requires and the B that it requires. So Y equals 0.09x minus 175.011. It's asking for the correlation coefficient. I really don't mind whether you put the r squared or the r, okay? So pick one of those and write it down. This is really sort of a measure of how well does the data match the points. For some of them, like linear, it'll give it to you in terms of r. For others, it'll give it to you in terms of r squared. In either case, okay, in either case, it will turn out that the r value is between 0 and 1. If it's closer to 0, then it's not a good fit. And if it's much closer to 1, it's a fantastic fit. If it's exactly 1, it's a perfect fit. And then on the worksheet, it's asking for an exponential line of best fit. So I'm going to do the same sort of thing. I'm going to type the y sub 1. I'm going to put as approximately. All right. And if you have to, you flip back on your notes to find the exponential equation. It's ab raised to the x sub 1. Okay. Now, visually, okay, take a look at the blue line versus the green curve, right? I think you can tell right away that the green one looks better. All right. Here is the correlation coefficient that the paper is asking for. All right, here's your A value and your B value. So this really funky looking number, 3.3 times 10 to the negative 32 times 1.04 to the x. In this case, the correlation coefficient is given in r squared, 0.9881. If you took the square root of that, you would get that r is 0.994, right? It's a little easier to compare which is better or worse if they're both in terms of r or they're both in terms of r squared. In this case, I would say that the exponential is the better fit, and it's because it has a higher r value. Higher r value. Also, you could say appearance. If you have it actually graphed and you see those two lines like on top of your dots, one of them just lines up better than the other one. Okay, heading back to Desmos, we're going to type in these, and it's only asking for a trigonometric month and average water temperature. Here we go. Okay, so there's the data for the second table. I'm going to hit the little zoom fit button down here so that I can see it all. All right, now you can see that it maybe kind of looks like a downward facing parabola, but the worksheet itself says let's do a trigonometric regression in sine. Okay, so coming to a brand new line, and I'm going to hit y sub 1 is approximate. And then you have to know what the equation of a trig function looks like. So it's a sine in parentheses bx minus, bx sub 1. See, forget the x sub 1, it won't work. Minus c plus d. Right? And again, it comes up with this gorgeous red trig function that tries its best to go through all the green dots. There's the correlation coefficient you can see. On the worksheet, it's asking what would be the water temperature on New Year's Day. So check this out. You can click on the graph and drag. So it kind of makes sense that right here, right, New Year's Day would be the very beginning of the year. You get 61.72. All right, and then it also says, using your equation, estimate the water temperature on the 4th of July. Okay, so 4th of July is a little after the 7th month, right? Here's the start of the 7th month. I want just a little bit more. So I'm saying it's like 65.9. All right, again, just a little more than 7. I don't know, 6. I can't find it. I had it as, there we go. How about that? 65.9. Right? Just a touch more than month 7. Again, it's an estimate. Right? And then the very last question, why shouldn't we use quadratic regression? I can speak. It doesn't fit the points. All right? Because notice this is starting to come back up, right? And a quadratic would go down forever. Water temperatures are not going down forever. It's called global warming. Thanks for the meow, cat.